Hello, everyone. Thanks for your patience. We are having today a very special AIDA Excellence Lecture. Thank you for being here. Thank you for attending this lecture. As you know, AIDA is organizing frequently on Tuesdays at 5 p.m. CET. Not every Tuesdays, but frequently we are having these kind of lectures on different topics. And the last lecture of this natural year is important, I think, lecture because of the research domains we are involved in here in this lecture is about quantum AI. So you know that quantum computing and artificial intelligence are two really, really competitive and important fields for research and also for innovation. And we wanted to have this kind of presentation because I'm sure that you all are having questions and doubts and you are intrigued by how we can mix and how we can improve these two domains together. So for doing this, we have today, we are really pleased to have Professor Francisco Chicano from the University of Malaga in Spain. Francisco Chicano is a full professor at the University of Malaga, and he has been very active in the last years on these combined topics of artificial intelligence and quantum computing, also separately, but also in the mix of them. He has a long experience in researching with projects, PhD theses, innovation with companies, transference from academy to industry. He's very active in organizing workshops, conferences, and international events. He's very active also in publishing in important journals and conferences, and also in editorial works and services for the community. So his background in AI and quantum computing is long and deep. And then I'm really pleased to introduce you, Professor Chicano. We will have a presentation of less than 1 hour so that you all have the opportunity to make your questions. Please feel free to make questions in the chat. Write there any questions you might have during the presentation. And also you can intervene at the end of the presentation if you want to raise your hand or just make your question yourself, or keep writing in the chat. We will be reading this question at the end of the presentation to Professor Chicano, and he will be answering them. So no more delays. Let's go right there for the presentation. Thanks a lot for being here, Professor Chicano. The floor is yours.
Well, first of all, thank you very much for the invitation. Thank you, Effie. Thank you, Enrique Alba, because it is a big pleasure for me, and it is a big honor to be part of, to participate in this series of excellent lectures, which I think is a very nice initiative. So I guess you should now see my screen, and perfect. Okay, so well, I'm Francisco Chicano. I come from the NEO research group in the Institute of Software Engineering and Technology at the University of Malaga. And well, the talk today will combine quantum computing and artificial intelligence. This is the outline of my presentation. First, I will put a very fast slide on what is the intersection between these two to try to explain where the talk is about. And also, I will do a very fast introduction to quantum computing. I assume no knowledge or little knowledge of quantum computing. I assume that probably most of the audience know about optimization and machine learning. These are the only probably artificial intelligence techniques that I will not cover, but I will say something about them. So then I will talk about two big things. The first one is how can we use quantum computing in artificial intelligence? And the second one is how can we use classical artificial intelligence in quantum computing? So these are the main two parts of the talk today. Then finally, some conclusions. So let's start with the intersection of these two disciplines. So artificial intelligence and quantum computing are both separate, they're very important disciplines. Artificial intelligence is very old, it's more than 80 years old now. And quantum computing is not so old, it's from the 80s. The ideas are from the 80s, but there were some developments in the theory in the 90s. And it's right now where there are machines that are able to do what the people in the 80s and 90s thought that could be possible. So it's now starting. So we are in what is called the noisy intermediate scale area, which means that we have machines that have a lot of noise, and it's difficult to do quantum computing because we have a very few number of qubits in the machines. They are very noisy. So we still need to solve many engineering challenges there, but it seems that in the next 10 to 15 years, we will have computers to do quantum computers that are able to do very nice things. So what I will talk today is how can we use quantum computing in the context of artificial intelligence? How can this arrow can be done? So how can we use the quantum computers for doing optimization or to improve machine learning? And then in the second part, I will talk how the classical artificial intelligence, machine learning or optimization can help quantum computing to improve the field of quantum computing or decide better circuits, algorithms, etc. But first, a few words about the quantum world, quantum physics. So in classical physics, the idea when we think in a system, the systems are in particular states, and as the time passes, the state are changing. The system state is jumping from one to another. I put here some discrete states, assuming that we have perhaps like a bit or a string bit, but we can generalize this and think that this state is the position of an electron in space, for example. And at each moment, this electron is in a different position, and this could be a different state, right? So this can be generalized. I will focus on the discrete case because this is what quantum computers do. Then what happened at the beginning of the 20th century is that as we started to look at smaller systems, physicists realized that the world is not like this. In the world, the system can be in a superposition of all these basic states. And the way in which they represent this is that imagine that we have all these states. These symbols are called, this is the Dirac notation. This represents the basis vectors. But yeah, they are symbols labeling the different states. And at the end, what is a state of my system is a weighted sum of all these possible states of the system, of the classical system. And the weights are not real numbers, they are complex numbers. That's why I use 2 dimensions here to distinguish the different values. I use the size. The size can be imagined like the magnitude of complex number, and the color, which can be imagined as the phase of that complex number. As the time progresses, this state is evolving, and then we will have different complex numbers in front of these basis states. This is how the quantum world works. But there is something more interesting. When I take a look to the system, when I have here a superposition, I don't see the superposition. As soon as I do a measurement, I only get one of the possible values, one of the possible states. Which one? We don't know. So this is completely random. What we can say is what is the probability of obtaining each of these. And the probability is proportional to the square of the modulus of the magnitude of these numbers, of this complex number. But I get only one. I don't know which one I will get. So usually in quantum computing, probably if you have done something, you have seen that we have to do many shots. And these shots are repetition of the same experiment. We run the same circuit one and other time, many times. And at the end, we have a probability distribution of all the possible outcomes. So when we go when we want to apply this in computing, if we imagine classical computers as classical mechanic systems, then imagine that we have the minimum amount of information, the bit. If you have a bit, you have only 2 states, 0, 1. if you have 2 bits, you can have 4 different states, 0, 0, 0, 1, 1, 0, and 1, 1. And this is how classical computing works. But in the case of the quantum computers, we don't have bits. We have qubits. We call qubits because of quantum bits. And in a qubit can be, we can have superposition of states. We can have 0, we can have 1, but we can also have a superposition of these 2 states. If we have 2 qubits, then we can have 0, 0, we can have 0, 1, we can have 1, 0, we can have 1, 1, but we also can have a superposition of these 4 states. So we need a vector space to represent vector complex, because all these numbers are complex, space to represent the state of the quantum machine, okay? Okay, so how can we use this to do computation? So imagine that we have a quantum machine, and this is one of the probably the bad news at the moment is that we have to implement the algorithm using very low-level tools. You can imagine that if you are programming or you program, or imagine that you are said that you have to write your algorithm using logical gates, and, not, or. So this is what we have at the moment in quantum computing. We have to implement algorithms building quantum circuits, and the quantum circuits are just gates, quantum gates that we apply to the different qubits. So these are the qubits. These are gates. I will not enter into the details, but this is the control node. This is a node, and this circuit at the end, what does is to increment by 1 the input that we have, assuming that this is an integer, a binary representation of an integer number. So imagine that we have as input this value, 0, 0, 1, 0, that we provide to this quantum circuit. And if we run this circuit over this input, what I get is 0, 0, 1, 1, which is this circuit is increasing by 1 the value of the input. So this input is 2 in binary representation. If I increase it by 1, I will get 3 in binary representation. Okay. The nice thing is that what happens if I use as input a superposition of 2 values, 0, 0, 1, 0 and 0, 1, 1, 0. This is 2 and 6 in binary representation. If I apply this quantum circuit, I will get 0, 0, 1, 1 and 0, 1, 1, 1, which is 3 and 7. So if I start from a superposition of 2 different states and I apply the quantum circuit once, I will get a superposition of the 2 outputs that I would get if I run the algorithm over each of the inputs separately. So this is a kind of parallelism, because it's like running this circuit over each input in parallel and then joining all the results. But I only had to apply this circuit once. So it's a kind of, it is called quantum parallelism. But I put a question mark, and I put a question mark because now we come with a bad news, and is that if I try to measure what I have at the output, I will get only one answer. One of these 2 will disappear, and I will only see one of the outputs. And this is because, if you saw my previous slide, I have a superposition of all these states, but when I measure, I only get one answer. So this is the bad news, and this is what things are not so easy. And then probably you have heard that quantum computer is very good and can run many algorithms faster than in classical computer. But if you look at some serious publication, they say, no, this is not so easy, and there are some limitations. This is one of the main limitations. So when we want to use quantum computers to speed up algorithms, we have to think in how to design the quantum circuit in such a way that the probability of having the desired output is maximized. This is what we have to think about in this context. So if we want to use quantum computers in machine learning, or we want to use it in optimization, we have to be sure that the probability distribution we get after measuring many, many times, in this probability distribution, the desired outputs, the values I want to have, appear with higher probability than the others. And this is Today, this is quantum programming for optimization for artificial intelligence in general, okay? So this is the short introduction to quantum computing. Now I will cover the first part of the talk, which is how can we use quantum computing in artificial intelligence, and in particular in two domains, optimization and machine learning. So let's start with optimization. And probably you have solved this kind of problem in the high school. You have a function, in this case a polynomial, and you are asked to compute what are the minimum and maxima of this function. And a local maximum is a solution where a point where that is higher in the value of the polynomial is higher than the neighbors. And a local minimum is a solution where the values of the polynomial are lower than the ones in the neighborhood. If we take this position here, this solution here is the global minimum because it's having the lowest value. And this is usually in optimization what we want. We want a global minimum or a global maximum of some function. In this case, it is easy. There are some not so easy cases like this one, the Ackley function. It has still an expression that can be evaluated, but it has many local optimum, many local minima in this case. It is not easy for an algorithm to get the global minima because there are many, so there are exponentially many. But if we go to the discrete world, in combinatorial optimization, we have some other problems that are even more difficult than continuous one. One example is the 0-1 knapsack problem, where we have a knapsack here with a maximum capacity, 15 kilograms, and we want to maximize the value of the object that we put inside, but we have a limitation. We cannot put inside more objects than the capacity that the knapsack has. So we have 15 kilograms, so the sum of the weights of the object I put inside should be lower than that. And we have another problem, which is the vehicle routing problem, very popular for delivering companies, is that I have a depot. I have a lot of goods that I have to deliver to the customers, and I have to create some routes, optimal routes, trying to minimize cost or minimize time to deliver all the goods to all the customers. So these are two examples of combinatorial optimization problems. So in the context of quantum computing, there is a very famous, very popular algorithm that is the quantum approximate optimization algorithm. It was developed 11 years ago by Farhi, Goldstone, and Gottman. And the idea of this algorithm is that I create a parameterized circuit. So it's a circuit that depends on the objective function I want to maximize or minimize, but also it depends on some parameters, gamma and beta here. And the algorithm works like follows. As we have this parameter circuit that I know that it will have at the end, we will have here a quantum state. We measure many times this output, and with this measurement, I can compute the average of the objective function for all the sample solutions. This is an approximation of the average value of F. This is the input for a classical algorithm that proposes new values for these parameters. When I change these parameters, I will change this state, and this will change the probability distribution of the output. And the goal of the classical optimization algorithm is to maximize this average. If I maximize this average, most probably I will have a probability distribution at the output where the global solution, the global optimal solution appears with a high frequency, which is what I mentioned before. It's like programming in the quantum world is trying to maximize the probability that the output I desire appears in the circuit as a sample of the circuit. If we look inside this parameterized circuit, we find that there are three kinds of layers. We have this kind of layer. This H gate is called the Hadamard gate. What makes is this is a zero state, and after the Hadamard gate, I have a superposition of the two possible basis states, 0 and 1, with the same probability of appearing each of them. So after applying this, I will do a simulation of this step by step, and after applying the first layer of Hadamard gates, I will get this probability distribution. This is not probability distribution, it's amplitude. So we can see here the complex numbers associated to each of the different bit strings of the states. We have the same, we see that we have the same weights for all the possibilities. Once I apply this problem-dependent part, the orange block depends on the objective function. What happens is that the phase of the complex numbers changes depending on the objective function. In this case, in this particular case, the purple values here have a higher phase. This means that they have better solution for my optimization problem, while the green ones here in the corners, these are the having a lower phase, which also means that they have a lower value for the fitness function. We don't want this because they are minimizing the objective function. So we want to maximize the objective function. We want to increase the probability of these purple solutions, right? But this is the phase. If I measure now, I will get any of these answers with the same probability. I need something else. And this is what the second layer, the green layer, which is called mixer, is doing. So if I apply the mixer now, what happens is that the big string having the higher phase, now this phase transforms into amplitudes and magnitude of the complex number, and they have a higher probability of appearing as an output, while the ones having lower fitness, lower phase, is decreasing the probability of appearing as after a sample. I can do this many times, and in particular, the QAA does this many times. This is a parameter of the algorithm. You can decide how many times you do it. After doing it twice, we get this, and if we sum the probabilities of this solution that are here, 0010, 0011, and all these, they are optimal solution to this problem. If you sum the probabilities more than 80%. So with more than 80%, I will get a global optimal solution for this very simple toy problem, right? So this is how QAA works. This is how it works and how it is used in optimization. It is a very popular algorithm. There are more than 750 papers on QA, probably more now because this was this statistic from July. And there are many variants, 17 variants identified in a survey from the last year. And there are even some proofs, some theorems proving that has some quantum supremacy. But the quantum supremacy, the quantum supremacy result says this: the probability distribution that we obtain after sampling this ansatz, the QAA ansatz, cannot be obtained efficiently in polynomial tuning with a classical computer. The thing is that, and this is a critical part now. So the thing is this the kind of quantum supremacy we expect to have for an optimization algorithm? Well, we have doubts of that. The reason is that when we want to optimize, when we want to find the optimal solution to a problem, we don't mind what is the probability distribution at the end. If it can be reproduced by a classical computer or not. What we want is the optimal solution. So we did theoretical work some months ago, and we tried to compute what is the runtime of QAA for linear functions. Linear functions are very easy to solve. So in particular, this is the linear function we use. It's a sum of this SL is a variable, which is S is because it's a spin variable, it's not a 0, 1 variable, but it's a -1, 1 value, can only take -1 or 1. Sorry. So the solution for this problem is very easy. If we want to maximize this, I only need to have positive values for the positive constant and negative values for the negative constant. So this is the solution, right? It's a very simple problem. It can be solved in linear time in any classical computer. So the thing is that when we use QAA for solving this is very easy to analyze theoretically because there is no interaction among qubits, and this makes things very easy. And we were able to prove a theorem that says that the QAA can take exponential time to solve this problem to optimality if it happens something, and this something that happens, we were able to prove that happens at least for p equals 1 and p equals 2. And we conjecture that this happens also for all the values of q. So this means that if we fix the number of layers of this algorithm, which is usual in particular in this area, in the niche area in which we are right now, The runtime of solving up to optimality this kind of linear function is exponential. And this is a particular expression, right? So this is very bad news for optimization. And we wanted to analyze what happens and what the literature says about that. And well, first we have to say that this only applies to linear function. With perhaps there are some NP-hard problems which are not particular linear function where QA can be solved, can be very competent. And in fact, there is a paper by Bullet, Nunn, and Montanaro that suggests that this algorithm, QA, may outperform classical algorithm for this problem, KSAT. But they also say that there is no proof of that. So as they say, no one has been yet shown an unambiguous advantage over the best classical algorithms. There is also another result in Harrow and Knapp in 2021 that proved that if we use black box setting, like QAA does, this requires this number of function calls, and this epsilon is the error. So if we want the optimality, probably this could take for infinite time to solve the problem. And then we thought perhaps we should take a look to the algorithms that we know that have a quantum advantage. One of these algorithms is Grover search. We know that Grover search is an algorithm that always can solve any classical problem, any classical search problem in square root of the classical time using a black box setting. The thing is that there is an extension of this algorithm, which is by Ashley Montanaro, to solve not only very unstructured search problem, but also problems that can be a search on a tree, like using backtracking. The problem is that there is a paper by Hoeffler in 2023 that say that quadratic speedup is not enough. The current GPUs could solve this kind of problem earlier than even the more optimistic quantum computers in the future. So it seems that Grover search or the extension of Ashley Montanaro is not enough to solve this kind of problems. So then the next step is, let's say, take a look to the Fourier transforms. Fourier transform is a problem. The discrete Fourier transform requires exponential time in a classical machine, but it's polynomial in quantum computers. So in fact, Shor's algorithm, which is an algorithm that is scary in the cybersecurity community, is based on the quantum Fourier transform, and is able to break the RSA keys. We also have the Deutsch-Jose algorithm and the Bernstein-Basirani algorithm. They are all based on Fourier transform, some other kind of Fourier transform, the Walsh-Hadamard transform, which is a group theoretic Fourier transform, and they have an exponential speedup. We also have some positive results in classical computing. In the context of gray box optimization, there are some operators, partition crossover, and we have some the use of group theoretic Fourier transform that has been applied in optimization, and we obtain some exponential speed up even in classical computing. So we think, okay, so perhaps the Fourier transform is the way to go. And recently is October 22, but this paper was published 1 year ago in Archive in Nature. It appears this paper using quantum Fourier transform to solve to speed up optimization. They were able, I will not enter into the detail. If you're interested, you can take a look to the paper. But basically what we do is that they prepare the system to maximize the probability of that I get the not the global optimum, but a very good solution at the output in the Fourier space. And then they apply a Fourier transform, and they automatically get, with very high probability, solutions that are very, very near the global optimum. They are able to prove that with this algorithm, they can solve in polynomial time, so they can approximate the solution to problem in polynomial time, and this approximation ratio is better than the classical algorithms. So I think this is a very nice result, pushing or using the Fourier transform in optimization, and that could be the way to go in optimization. Okay, so there are some other ways to do optimization in quantum computer. The second way, and probably the most popular one, because this is there are companies behind this and they are offering services on this, is the quantum annealers. Quantum annealers are based in the very old theorem, the adiabatic theorem by Born and Fock, 1928. The idea is that if We have, well, Hamiltonian, probably you have seen the concept of Hamiltonian in many places. I don't know how familiar you are with Hamiltonians, but Hamiltonians are two things. They measure the energy, they are an expression that can measure the energy of the system, given a state. If you apply the Hamiltonian, you can get the energy of that system. But they also are part of the Schrödinger equation that tells you how the system evolves with time. So the idea of this theorem is that if you have a system, a quantum system in the minimum energy state, the ground state, and you evolve this system, you change the Hamiltonian very slowly, it will always be in the ground state of any Hamiltonian you have in the middle. So the idea of the quantum annealers is that we start with the ground state of a well-known Hamiltonian. I know the Hamiltonian, I know the ground state. I put my system in the ground state of that Hamiltonian, and I change the Hamiltonian to be similar to my objective function. If I do this change slowly enough, then I will have the ground state of my problem, which is the state minimizing my fitness, my objective function. So I will get the global optimal solution. This is what the idea behind the quantum annealers. QAOA is inspired in this idea also. So, but I will not enter into these details, but there is a proof, we can prove mathematically that QAOA is an extension, is a discretization of this process. In the case of quantum annealers, what we need to do is to compute, to create an objective function that has this shape. It has an Ising model. So I have to transform my optimization problem into an Ising model. There is a systematic way to do that. There are some different ways of doing it, and it's not completely clear what is the best way to do it, but there is a systematic way to do it. And once I have this, I have to do minor embedding because the quantum annealers have many qubits, have 5,000 qubits typically right now, at least the ones by the wave, but they are not all of them connected among them. So sometimes I have to assign one of these variables to many of these qubits at the same time, and there are many ways of doing this. So this process of transforming the Ising or translating the Ising model into the topology of my quantum annealer is called minor embedding, as in an NP-hard optimization problem. So this is a very difficult problem. I will just mention this because we will see later in the second part of the talk how this can be done using machine learning. Okay, so let's go for machine learning. In the case of machine learning, well, so a very short introduction. The idea, I will focus only in supervised learning. And the idea is that we have a data set with the features and expected value, the value I want to predict. And during the training phase, I use this data to create a model. It could be a neural network, a super vector machine, for example, a logistic model or a regression model, linear model, for example. And during the evaluation phase, I want this model to predict what is the expected value of a feature for which I don't have the expected value. So in AIDA, we have many images of radiographies of the lung, and I want the model to predict if there is pneumonia or not in that lung. So then what I would do in the evaluation phase is that I only present the image of the lung, and I ask the model, does it have pneumonia? And it says yes or no, okay? So one of these models is the classical neural networks, where we have a network of neurons, and each neuron takes several inputs. These are real numbers in general. They are weighted with a weight that is associated to each edge of the network. The edges have these weights, which are synaptic connections and which can be changed during the training phase. And after summing the weighted sums of these weights with the inputs, we apply a function. This is the output of the neuron. And in a neural network, we have many of these neurons, and we have an input layer where we put the feature of the input. Then the information or the computation is translated into the right here. And at the end, I have an output with a prediction. This is a classical neural network. Probably all of you have seen this before. How can we do the same in a quantum machine, in quantum computers? We have the concept of quantum neural network. The idea is to replace this classical name of the word, by a parameterized circuit. In this parameterized circuit, it works very similar to QoA. We have a parameterized circuit, we have a circuit with different parameters, and we have some features of the input. And when I want to train this, what I do is that I introduce the input data here, I introduce the parameters, I build the circuit, and I run this many times. Each time I measure, I compare the value I have with the expected value. We apply a loss function, and with the training error, I can guide a classical optimization algorithm to propose new values. So it was quite similar to how QoA works. So it's optimizing, because at the end, training is optimization, right? Okay, so what is inside this parameterized circuit? This time we have two parts. We have the data encoding. There are many different ways of encoding the data. I will show some examples very fast next. And we have a quantum algorithm part. Then we measure and we apply the classical technique here to propose new values for the parameters only, not for the data. And there is something interesting here, and is that we can also have access to gradient information. We can compute the gradient of the functions. You can imagine it's not easy. So in a quantum algorithm, if you are running an algorithm like this in a machine, you don't have access to the inside. You cannot stop the algorithm and see what is inside and compute things. So there is a way to compute the gradient without stopping the machine, and it's this parameter shift rule. So we can compute the gradient using this function, and this function, by the way in which it is designed, the circuit, is always true. So it's a trick to compute the gradient without having access to the inside of the quantum algorithm. These are different ways of encoding the inputs. We can use very basic basis encoding, in which so the different vectors are just mapped into an input vector for the quantum machine. We could also use each value could be a phase for one of the states of the superposition, basis states, or we can use amplitude encoding, where we have different basis states, and they are weighted by this magnitude, the magnitude of the value that we have. So these are different encodings. They have all advantages and limitations, so it depends on the application you want to apply. Then the quantum algorithm is typically based on rotations. These gates are rotations, so it's a kind of rotation. I didn't introduce the block sphere, but the ones that know about quantum computing, this is a rotation in the block sphere around the y-axis. We also have some some control node gates here. Okay, so this is just how can be applied machine learning, and I go to the second part of the talk, where I would like to talk about how can we use the classical artificial intelligence techniques in quantum computing. This is not new. There is even a book, this book by Lee Spector, more than 20 years ago, on how to apply, in this case, genetic programming to design quantum circuits. So this is one of the first applications I would like to talk about. How can we use optimization, classical optimization in particular, meta-heuristic and genetic programming in particular, to design quantum circuits? Genetic programming is a kind of evolutionary algorithm. In evolutionary algorithm, we have a set of solutions, which is called population. And each solution in this set of solutions in iterative process are changed using recombination, which combine features of the different solutions to create new solutions, and also do small changes in the solution, which is called an operator called mutation. And after iterating, we get new solutions that replace the old one that was, and this iterates until we have a good set of output solutions. So this is a very old paper, but recently in a master thesis here in Malaga, we applied this genetic programming, but also a special case of genetic programming, a grammar-based genetic programming, to design quantum oracles for the Grover search. And what we found is that this is an example of circuit that was generated using some systematic methods published in the literature 2 years ago for computing the multiples of 3 oracles. So this circuit that you see here in 2 lines is computing is marking the states that are multiple of 3. And you can see here how many gates it has. These are single gates. These are complex gates with more gates inside. It has 4 qubits here, but it also have 4 extra qubits needed to do the computation. So it's a very complex circuit. While applying genetic programming, we were able to find this one doing exactly the same thing. So the depth is lower, which is very nice, especially now, because if you have lower depth for computing a lower number of gates, you can run the algorithm faster. And this is critical in the niche area where we have problems like decoherence or something like that, noise. So we need very short circuits. So this is great for this application. And we can see we also apply this technique to different oracles. And in all the cases, we were able to beat the depth, to reduce the depth of the circuits, equivalent circuit that we find in the literature. So applying optimization and genetic programming, in particular in this case, evolutionary algorithms to design circuits, to optimize circuits is a good way to go. The second example I would like to explain is how can we use machine learning for, in this case, circuit transpilation and the assignment of logical qubits to physical qubits. The idea here is when I have a quantum circuit, we have to decide which logical qubit is going to each of the physical qubits. This is not a trivial task because the different physical qubits are connected in a different way depending on the topology. So if I do a bad assignment, I have to introduce many gates in the circuit, in the intermediate circuit, and this means larger depth and more noise and more an output that is less with lower fidelity. So there is a heuristic, and this is included in the Qiskit library by IBM, that is able to take into account the noise of the machines, is able to take into account the topology and all these features to do a very good assignment of the logical qubit to the physical qubit. The problem is that this heuristic is very slow. So what we did is, why not apply machine learning, try to learn what the heuristic is doing and run just a model. So the features that we have is, as I mentioned, the data from the machine, the noise, the machine calibration details. We also have the topology of the machine, and we also have information on the quantum circuit. These are the features, and we want the model to predict what is the optimal assignment from the logical qubit to the physical qubit. We also apply some evolutionary methods to decide what is this model. So this model is a neural network, a deep neural network, but the architecture of the neural network was decided by an evolutionary algorithm in this case. And well, finally, the results were very good, and they were able to reproduce the result of the heuristic, but in a very short time, which is critical for this kind of applications. Then another example, and this is so I only have 2 more, so, and I'm done. The next sample is a minor embedding. So how could this problem of assigning each of the spin variables to the different physical qubit is a complex one, is NP-hard. And there is a paper 1 year ago that apply reinforcement learning to do this. This is a very complex optimization problem, and they can profit from reinforcement learning to improve in this process. And the last example is again from Google AI, again published in Nature. Probably this is a paper that was very in the quantum community. The quantum computing community was very popular at the beginning of this year, in January, February, or March 2025. I don't remember exactly the month, but was published a few months earlier. Well, the idea is that they use neural networks to decode or to apply the decoder, to implement the decoder of an error correction method. So well, let me explain first what is the problem here. The problem is that I have said that each physical qubit has a lot of noise. So what they implemented from the 90s is quantum error correction. The idea of quantum error correction is the same idea as in classical error correction. We use not one qubit to represent one physical qubit to represent one logical qubit, but we use many of them. In particular, they use here 49 physical qubits to represent one logical qubit. But these 49 are split in two kinds of qubits. The orange ones, the data qubits, are really containing information, and the measure qubit, the blue ones, are qubits that are not used to measure information. They are redundant. They are trying to check if there is any problem with the other qubit, with the data qubits. So what they do is that from time to time, and from time to time means 1 million times per second, so every microsecond, they measure these measurement qubits, and they see if there is an error or not. If all of them are zero, everything is okay. But if there are some of them that are not zero, like for example, these ones, this red means that there is a one here, there is a one here, then there is a problem here. There is one of the qubits is failing, and they have to decide which are the qubits which are failing, which are changed, and they have to mitigate that error. They have to do this very fast because, as I said, it's 1 million times per second. So in 1 microsecond, they have to decide which are the qubits which are wrong. And this problem, deciding which are the qubits which are wrong when they have this kind of surface code, is an NP-hard problem. So what they did is to train a neural network to solve this optimization problem, and they were able to outperform with a neural network the other method, which is a classical matching algorithm, which can be solved in polynomial time, the problem, but it's an approximation. And with the neural network, they were able to improve the result of the matching algorithm. So this was done by Google AI at the beginning of this year. And this is the end of the talk. So the conclusion that we get is that starting by the second part, the use of artificial intelligence in quantum computing is essential in many steps. In particular, we have seen with the last example that if we want fault-tolerant quantum computers, we need quantum error correction, and this is done so frequently that we need very efficient methods, and neural networks are one of these very efficient methods. And also in the other side, the use of quantum computing to speed up processing AI, especially in optimization, there are many companies that are now selling these services. D-Wave is a very big company that is now having quantum annealers. Fujitsu is also building another quantum annealer, and optimization is seen as one of the big promises where quantum computers can be used to sell and to solve some problems more efficiently than in classical computers. This is the end of my talk. Thank you very much for your attention. I'm happy to answer any question that I could answer.
Thanks a lot for this. It was excellent. Thanks a lot for the detailed presentation. So many options, so many ideas, so many contents. I would just open the question part and answers by asking you maybe if you can give us just the name maybe of software that we can use, like Python libraries, simulators, just names, just to guide the audience. And maybe also quantum computers where people can have an account for starting their tests. Thanks a lot for that.
Yeah, well, I think there is a very popular library and also simulators, and which is IBM Qiskit. So IBM is putting a lot of effort in training and also in building open source tools. And the Qiskit library is one of the excellent tools they have. It includes many simulators inside, but you could also access to the IBM quantum machines. They have machines up to 400 qubits right now. I think that when you can have access to the top machines usually with a free account, but you can access to machines with having more than 100 qubits for sure, and you can do it with this library. So this is one of the good ones. There is also a platform, Penny Lane, that is also very good for simulation. And probably this is the big two names in gate-based quantum computers. If you are more interested in optimization, D-Wave used to have free accounts. Now it's not so free. So now it costs, it has some cost and it's not cheap. But usually they had some, in the past, they had some times and then some 1 minute per month you could apply for. And they have a tool, which is Ocean, a library, Ocean, that is doing the same as they are doing with Qiskit, but for the quantum world. In this case, it's more proprietary, so they are selling their services and they are not so free. But if I have to highlight one and you're interested in gate-based quantum computer, I would say Qiskit and IBM, all the resources that IBM have, the courses and all that, I think it's excellent.
Okay, thanks a lot for your answer. Very useful. Now we have a question there, which is it's really in two parts. The first part of the question is, what is the role of the mixer in the parameterized circuit? Can you explain it again shortly?
Yeah, sure. So, well, I will go back. So I can do also this again. So imagine that you have the problem-dependent part just marked with a phase, the different states. And this phase is proportional to the fitness. And the mixer translates this phase into a magnitude. So it's doing the translation between the phase that you have into a magnitude. So you can see here this purple, which has the highest phase. Now, when I apply the mixer, is increasing the magnitude of the complex number that is in that state. So it has the effect of increasing the probability of having very good solution or decreasing the probability of having very bad solutions. This is the role of the mixer.
Okay, thank you. Clear. Then the other part of the question is this: is the input data in the quantum neural network classic data that one encodes to qubits for the quantum algorithms? I think this is yes, the answer. But what are the encoding schemes available?
Yeah, so it's a very good question because I didn't cover everything here. I didn't have the time, but here, there's 3 examples. If you go to the IBM page where they have training on this, you can find at least 5 different ways of representing the data. And this is classical data. But there is another field, I didn't talk about this, on how to use quantum computers for quantum data. And in this case, you can imagine that there are quantum sensors. Quantum metrology is a very popular topic now. And you could have some information that are coming from quantum sensor, which is quantum. So you have a superposition of values. And you could apply quantum neural network to this quantum data, not classical data. This is a different, completely different topic. I didn't cover this here. But yeah, there are many different schemes. In this case, these 2 schemes, for example, the size of the number of qubits we need is in the length is exactly the same as the length of the data, but for the amplitude encoding is the logarithm of the length of the data because we use if we have n in log n we have different log n possibilities here, and we can use the amplitude encoder for that. So and these are only 3 examples, but as I mentioned, if you go to the IBM webpage, you can see much more.
Okay, thanks a lot for that. Then we have another question, which is a question about minor embedding. And the question is, what is the difference with respect to quantum annealing? Where is the name coming from for minor embedding?
Well, it's a mathematical problem. So the minor embedding this is a graph problem. Minor embedding is, the idea of minor embedding is if you have a graph, a very small graph, and you have a larger graph, but it's not the same structure, how can you map the smaller graph into the larger graph? And this is called minor embedding in maths. And when you have to do this, you can imagine that this Ising model is a small graph that you have to embed into a large graph, which is the topology of the quantum machine. That's why minor embedding comes in the name. Yes.
Okay, thank you. Then we have two more questions. One is, well, the Masin is really interested in your presentation. He is a bachelor student. He's asking for topics, papers, problems worth diving in, but I'm not sure that an answer here should be appropriate. So maybe Marcin
You
can
can write
contact
me.
you.
Yeah,
Yeah.
yeah, sure. You can write in my email. My email is in the presentation. The presentation will be available in the next days, I guess, in the webpage. So yeah,
Yes.
it is. Yeah,
Okay.
it is.
Yeah, Martin, please send Professor Chicano an email, and he will be happy to make an answer with what you're asking about topics, papers, or problems to dive in. There are lots of comments thanking you for the presentation, which is wonderful. And then there's another question here, which is how many parameters can quantum computing algorithms optimize? Is there a limit? Light neural network have 10 millions of parameters.
Well, right now we are not at that level of classical neural network, right? So as I mentioned, the largest quantum computer now have between half and 1,000 qubits. This is not enough to do fault-tolerant quantum computing. We need millions or tens of millions. So at this time, any computation you can imagine probably is more efficient than in a classical computer right now. But well, the future, we assume that in 10 or 15 years, there will be more possibilities. In the case of optimization and quantum annealers, we have machines with thousands of qubits. And there is a topic called quantum distributed computing. The idea here is that if you have a very big problem that doesn't fit in one machine, you can split it. And you can solve part of these problems in different quantum machines and then combine the result and get the answer that a biggest machine, a largest machine could have provided to you. So these are also a very hot topic right now, how to split the problem.
Yeah, divide and conquer is always a very nice
Yeah.
tool in science. Thanks a lot for that. Well, I was having the impression that there are many topics to do research on for using quantum computers, using them, let's say, like coprocessors for classical algorithms look like promising way to go, maybe because you are presenting always the classical algorithm
Yeah.
and being helped by the quantum computer?
Sure, this is a also very hot topic. So there is a research group here near here in Spain, Extremadura. They are working on the service path, how to combine quantum and classical computing at the service level, and what are the from the point of software engineering, how to design that and all that. And this is a very promising. Of course, quantum computer will not replace classical computers. They will be at most a coprocessor. But the problem is that right now the quantum computer need very particular, so they are refrigerators basically. So there is a small part there, and if you have seen an image of quantum computer, it's like it's like a very big thing that is, but most of this thing is a refrigerator, and you only have a tiny part of
Big,
which is the quantum.
big freezer, small
Yeah,
meat inside.
yeah, exactly. So it's like this. So it's difficult at the moment with the technology that we have. It could be a coprocessor in our
Yeah.
laptop.
Yeah,
So
definitely amazing times coming. And a very last question, because we're out of time now. And the question is, did Professor Chicano run his simulation related to his paper on QAOA in 25 on D-Wave quantum annealer computer? Did he prove that QAOA is not necessarily the optimal algorithm even for linear functions?
So there is no simulation. So it's a theoretical result. So it's a proof. So we were able to prove that the runtime is exponential. So so we didn't do. So we only did math. So it's not. So there is no run that can improve that. So it's math, and the
It's a
result
proof.
is
So it's a proof.
yeah.
Everything
Yeah.
is done. Okay. Well, I think we arrived at the end of the talk. It was really excellent. I was really enjoying every single present part of the presentation and your answers also. We have many comments on the chat about how nice it was and how informative. Thank you all, the audience, for being here. Thank you for these questions. It was wonderful to have again a new AIDA lecture. We will meet again, hopefully. Tell to your colleagues and friends we are holding these lectures, and we will come back in January. Keep tuned. Thanks, Professor Chicano, for this wonderful presentation. Bye
Thank
bye
you for
to
the
everyone.
invitation. Thank you. Bye bye.
Bye.